Okay, so this is my Excel file that I use to simulate the effect of giving. Here I have 24 tests. So let's just scroll down. You can see I have 24 tests here. For each test I have the true positive rate and the false positive rate. And that's what you start with. So if you don't have 24 tests, not a problem. I'll show you how to change this in a second. You can set any base rates you want up, and you just type it in there. It really doesn't change distributions that much, but we'll just put 40% in. That's a very common idea about what percent of people in forensic neuropsych cases are faking. There's 10,000 cases here, so this goes down to 10,001 actually, since we have top row used for something else. But what we have is we have some random value here which decides if the person is a faker or a non-faker. And essentially the rule is simply if the base rate decides whether the person is going to be a faker or not. If you're higher than the base rate, you're going to be called a non-faker. If you're lower than the base rate, you're going to be called a faker. And so it's just randomly sampling here, and of course then the file is limited by the ability of Excel to generate random numbers. I'm not concerned about it because it's not that kind of precision that I'm interested in. But that's how it's decided. Once you get decided whether you're a faker or a non-faker over here in column J, then for each test we're going to generate another random number, which is I think down here somewhere. I forget how it works. That's not it. Let's just look again. If CL2, so let's look where CL2 is. CL2 is here. It's a random number. So to decide if the person got a positive score or negative score, again, we're going to go with another random generation, and then it's going to compare it to I forget how it works. But I forget how it works. But it basically uses random generations to decide if your score is positive or not. And then that depends on these values here. So if you change those values, then those things can change. And so then you just get a variety of false positives, negatives, true positives, so forth, based on the intersection of what category the person is in and what their score was. So here's a non-faker, they're positive, that's a false positive. Non-faker negative, that's a negative. We could call it a true negative, but I really wasn't interested in that when I made this data set here. This person was a faker and they got a positive score, so that's a true positive. And then all that happens here is these things just tote these things up and show you the distributions of them. Again, it all depends on these values here. Here's some redundancy built in. This shows what I told it to do in terms of assigning positive and negative scores. These are the actual rates. And then this shows you the distribution of false positives and true positives for that test. Okay, for that sample. Then the rest of, let's just talk about what this is. This is just your family-wise error rate whenever you have more than one null hypothesis, and then alpha isn't really 0.05 anymore. It gets higher and higher the more null hypothesis that you have. Here you have 24 null hypotheses. And so you can compute that. It's a standard formula I put in there, and it just says, tell us what the probability is of getting at least one false positive out of your 24 tests. Well, 96.2% probability. So what else do we have here? The base rate tells us how this is distributed. This tells me how many people out of 10,000 got no positive scores at all when we gave 24 tests. Only 216. So that the percent of non-fakers with any positive score is 96.4%, and we predicted it to be 96.2%. That they would get at least one positive score or more. This is your distribution of positive scores when you're not faking. Here's a little graph of that. Here's your distribution of positive scores when you are faking, and we can put them together to get this graph, which again, you resample just by, I usually just type 1 in an empty cell and hit enter. It resamples, the graph changes. Here, let's look at it here. So you can see that'll change. It's all dependent on what's thrown into these cells. And you see, this is how I do it. Okay, so do you need to have 24 scores to use this? No, you can just get rid of these and use 12. You just should always have them in order here, no gaps in these data. So you see the family-wise error rate changes when you get rid of 12 tests. It goes down. You can do it for just one test here. And you'll see that the family-wise error rate is predicted to be 19%, which is the false positive rate. And then everything else changes with it. So that should be helpful. If it's not helpful, let me know. I find mistakes in this thing from time to time. Mostly they're trivial mistakes. They're just not adding things exactly the way that they ought to be added. If you find a mistake, I would sure appreciate knowing about it. Most of this language, you just have to sit here and look at it and figure out what it is. There's a lot of extra stuff in here for things that I do from time to time. But this is the basic simulation that you would like to have. Let me know if you have any questions. Thanks. Bye.